I'm chair of this seminar today. And today, so we have a seminar by the Dr. Tomonaga from Riken, Japan. And he's actually a member of the Dr. Tide group, and he's working on the superconducting quantum electronics, especially for the superconducting quantum annealer and superconducting NISQ processor. So he will be talking about the architecture and the implementation for superconducting quantum annealer and NISQ circuit. So Tomonaga-san, please start, and you have a 25-minute talk and a 5-minute discussion. Yes, please start.
Okay. So thank you for your introduction, and also thank you to give me the opportunity to talk here. So my name is Akiyoshi Tomonaga, and I graduated at Tokyo University of Science in last year, and also I'm now postdoc in the side group Riken. So today, with the laser point. Okay. Today's topic is NISQ and quantum annealing. Firstly, I would like to introducing the annealing architecture in our laboratory. This is the partially full coupling quantum annealer. So this is my first job in my period of graduate student. This is published in the paper in JPSJ 2019. Title is Superconducting Quantum Annealing Architecture with LC Resonator. So this is the proposed circuit. Here is qubit, line qubit is here, and also qubit is coupled to the resonator. This orange one is resonator, and the resonator is coupled to the other resonator through this green coupler. And this resonator is coupled to the all other resonator listed here through the coupler, and then line qubit is coupled, fully coupled each other. This is we can call it partially full coupling unit of quantum annealer. And when we fabricated this kind of circuit in the with 8-bit chip in the real physical system, the size is around 1 centimeter square. Okay, firstly we consider to how to mapping the optimization problem this kind of circuit. So this kind of circuit with resonator, the Hamiltonian is a little bit different from the usual spin glass Hamiltonian. So of course there is a resonator part, bosonic resonator part here, and also the resonator interaction part here, and also there's a qubit spin part and spin D and spin dipole to the resonator magnetic field coupling here. But in this Hamiltonian can be fully diagonalized using the unitary transformation, and also diagonalizing the qubit part only is more easier. And unitary transform the qubit part can be written this one. So here is the sigma z part and sigma z interaction part. This is the normal spin glass Hamiltonian, and also here is the resonator part and resonator coupling term. Of course, this term also can be diagonalized, but this term is just can be treated by the offset of this Hamiltonian, this qubit Hamiltonian. Then we can ignore when we are processing the quantum annealing using this part. And Jrj can be derived from this equation. Jrj is equal to the 2gi and theta ij. Theta is a value that's satisfying this simultaneous equation. And using this simultaneous equation, when we are mapping the problem to the Jij, and then we can get the GCI. This is the coefficient of resonator coupling term, and also Gi is coupling term of the resonator and qubit, and also omega Ri is resonator frequency. And also, of course, next we need to consider about how implement it in real physical systems. So firstly, I would like to introduce about the superconducting quantum qubit as artificial spin. So this is a really famous paper in the D-wave systems. So D-wave system using this kind of flux qubit This qubit is composed of the two loops, main loops here and small loops here. This is separated by Josephson junction, and this kind of qubit is in this kind of qubit, the current is through to the left side and right side, saturation, and then we can define the spin up and spin down the same as the spin. And then we can use this kind of circuit as an artificial spin. And as same as this web system, we have using the flux qubit with two loops, one loop here and two main loops here. But the Josephson junction is we have the 5, and also the qubit is strongly coupled to the resonator through this coupling Josephson junction. Okay, firstly, we are thinking about the qubit, or only qubit. The qubit Hamiltonian can be written using this kind of circuit Hamiltonian, and Qi and Q2 and Q beta is a charge basis, Cooper pair charge between the in the Josephson junction, and this first this first term is corresponding to the charging energy of Josephson junction, and also the second term is come from the potential of the Josephson junction, EJ cosine pi I, pi 2, pi greater, sorry, yes, pi a little bit. Okay, and so this Hamiltonian can be controlled by this flux bias to this main loop and also alpha loop, and here is the F alpha and F alpha and F. We can controlling the energy of this circuit, and then after we diagonalize this Hamiltonian by numerically, we can obtain this kind of band structure. This band structure is plotted against the F in the main loop here. And when we control F alpha, we can changing this gap with delta I. And epsilon I here. Okay. When the first to second, here is the ground state, and also here is the first excited state, and here is the second excited state. And when the first excited state to the second excited state energy is much larger than the ground to the first excited state, we can treat this system as a two-level system. Then, after two-level approximation, we can get this kind of Hamiltonian of qubit using the power Z and power X operator. And F1, as I mentioned former, as delta I, the horizontal axis spin bias is controlled by F alpha, and epsilon 1 is the spin dipole can be controlled by F. Next, we need to consider about the coupling between qubit and resonator. And the qubit resonator coupling strengths can be calculated from this kind of formula. This is a resonator 0-point fluctuation current, and this is the current at the beta junction. And from this kind of formula, we can write the qubit resonator coupling Hamiltonian. This one. Here is the G1 sigma Z and A plus A. This is the same Hamiltonian. We introduced. I introduced formula in this slide. And G1 in this circuit, G1 is determined by the fabricated circuit parameters, but we can control in the Jij and through the GCI by coupler. I will talk it later. Now, okay. Now we are getting, we obtain this kind of spin glass Hamiltonian with this horizontal axis spin biases. And And we can need to consider this DIJ term. How can I map the annealing optimization problem in this GIJ? So firstly, GIJ is very roughly estimated to the nearly 4 times GCIJ as a condition of GI is nearly equal to omega R. This is the so-called deep strong coupling regime. This is a really special case. Coupling constant is equal to the resonant frequency. But this kind of regime is already experimentally implemented in this paper in 2017. And using this condition, at least we need to consider to prepare the normalized GIJ and epsilon I should be prepared -1 to 1. Maximum, and also the maximum GIJ is larger is better, but at least this is larger than, need to be larger than KBT is thermal population, thermal energy in the base temperature of the measurement. And all, of course, epsilon I and delta I and GIJ is must be tunable in time. And from the calculation of the circuit parameters, using circuit parameters, and also I estimate if the coupler enough to strong, minus 0.4 to 0.4 GHz, then we can prepare the annealing parameter of GIJ and epsilon minus I to I, minus 1 to 1, and GIJ is larger than around 200 MHz here. And this is one of the parameters we pass example of our circuit. The vertical axis is normalized annealing time 0 to 1, and the vertical axis is the circuit parameter is gigahertz. Okay. So I mentioned we need to, the coupler should be larger than, should be controlled by this 0.4 to 0.4, minus 0.4 to 0.4 gigahertz. And we are already implemented this kind of coupler circuit in this paper. And I will introduce it next slide. Okay, now we are considering how to implement the physical system of the coupler. So D-wave system using this kind of coupler. This kind of coupler is just the same structure as a square, and also the same structure of the qubit. And this coupler is, we can consider the tunable mutual inductance. Qubit is coupling through the this coupler mutually through the mutual inductance. And in the circuit QED, the important topic and important technology, the coupling between the resonator, coupling between the qubits to the resonator. This kind of coupling is very commonly used, and also the IBM circuit using this kind of circuit architecture. And the qubit is coupled to the two qubits is coupled to the resonator, and resonator frequency is different from each qubit. But qubit can be energy exchanged through the virtual photon exchange in this system. So in our circuit, we have the qubit and resonator and coupler and resonator qubit. This resonator coupler resonator part is our coupler. And also, as same as this kind of circuit, the resonator frequency is far apart. It's the qubit frequency is no problem. The resonator frequency is not affected to the physical phenomena in this coupling. Yeah, of course, qubit resonator frequency is affect to the coupling strength. Okay, so this is the our implementation of ultrastrong tunable coupler. So we have published this paper in the PR Applied in 2021. The title is ultrastrong tunable coupler between superconducting LC resonator. So in this circuit, this is the LC resonator, two LC resonator here, and the copper is here. So LC resonator shape is very flexible. We can extend the inductance limit to like this one. Also, we can simply making the compact circuit as like this one. Okay, this is a circuit previous slide I showed. This is the enlarged image of the coupler. This picture is taken by the SEM. And this is here is a meander line. This we clearly extending the line length using this kind of meander line here to increasing the mutual inductance between the resonator and the coupler. And junction is here, and here is the Josephson junction. This circuit is fabricated using the aluminum film. That Josephson junction is composed of aluminum oxide, aluminum sandwich. And measurements can be done using the vector network analyzer, pump frequency from the left side and through the sample, and through the sample here to here, its transmission signal can be detected from the port 2, or we can measure the reflection signal to here and reflected here, and to here and reflected here, and then we can obtain the reflection signal from at the port 2. Okay, this is the spectrum we can take using the vector network analyzer, and horizontal axis is the loop flux biases to these main loops here, and vertical axis is pump frequency from the vector network analyzer, and then the energy is absorbed when the system resonant frequency is applied. Then we can obtain this kind of spectrum, and we can see the two mode, one omega plus and also omega minus can be seen. So from this kind of spectrum, we can calculate the coupling constant between two resonators. Then we can obtain this kind of graph. This is the horizontal axis is the same as this normalized flux biases, and also vertical axis is the coupling constant between the resonators. Then we can obtain more than -1 GHz to around the 0.6 GHz. And I mentioned I need to -0.4 to 0.4 should be needed, and this one is including that kind of needed length. So using this kind of circuit, this kind of coupling circuit, we can preparing enough Jij, and of course we can prepare enough delta and epsilon I, and then we can prepare the annealing parameter for the mapping the optimization problem. Okay, next topic is NISQ, noisy intermediate scale quantum computer. And recently, the IBM and Google released a real physical system of many qubits, 45 qubits in Google. This is a famous paper in history showing some kind of quantum supremacy, and also now is most may have the most number of qubits having this Osprey chip. is 433 qubits. But this kind of complex 3D wiring technology is enabled to scale up the recent quantum processor. So this is for example, Osprey qubits from this kind of their homepage. The qubit layer and resonator layer and wiring layer is separated each other, and really fabrication technology is very sophisticated and very difficult to imitate from small laboratory and company. So we are introducing the new strategy for NISQ and surface core circuit using the all planar wiring. So this is we have published the paper in 2020, pseudo 2D superconducting quantum computing circuit for the surface code proposal and preliminary tests. Usually, the qubit layer is a single layer, and also the adding the pulse and readout signal. Within the readout signal, the other layer using to access each qubit. So of course, to consider the surface code, we need to square lattice of the qubits. In that case, we should access the center qubit from vertically access. But when we are using the origami structure, we can reshaping this structure, and we can access all qubits finally. So firstly, we are considering the qubit layer like this one in the surface code square lattice. Then extending the resonator and folding each other, folding. Then we can access the qubits using the external access is all access is can be done in the primary, and so that's a flexibility of the resonator shape is enabling to access reshaping this structure and accessing the primary qubit line. And this kind of overlap should be needed, but this kind of overlap is very easy to fabricate compared to the 3D wiring structure using that Airbridge, so-called Airbridges. Airbridge is like this one. This is fabricated using the niobium or aluminum and so on, and this is made by aluminum. We can using this kind of Airbridges. We can accessing the qubits by binary method, and also in the quantum annealing I showed before. Also, this kind of Airbridge technique can be used. And in this kind of structure, when we are considering the m equal 30, 30 means this line, 30 qubit is line. And this is the estimating size of practical one logical qubit. When we are considering the practical one logical qubit, the size that means for 900 qubit is in the same chip, and chip size is 30 and 2000 millimeter, and this is almost the same size of recent largest classical chip. Okay, and also recently recent progress of our NISQ target. Now we are fabricating the 100 qubit sample in this scale. And also, this is just fabricated. And we are now fabricating the 5 qubit and 10 qubit sample to showing some NISQ programs to, And this is a simple circuit and simple packaging and easy to fabricate. We can show in some results maybe next year or next year. Okay, plan is demonstrating for next plan is demonstrating for simple NISQ program in our circuit in 5 qubit or 10 qubit and extend. Later the extend 5 qubit sample to 10 or more qubit. And also we are focusing on bosonic quantum computing and also ultrastrong coupling and CNF junction and so on. So thank you for your listening. That is all of my talk.
So thank you very much. Very impressive talk, and actually that I was really impressed by your very interesting ultra-strong coupling, realization ultra-strong coupling, and also the very funny and to quasi 2D architecture, and you already realized 100 qubit NISQ processor. It's quite surprising. So anyway, so now open for the comment and discussion. So if you have questions, so please raise hand button or switch on your microphone. And okay, so Alex, please.
Oh, hi, thank you very much. My question is, how do you simulate the behavior of the system? So how do you check that it behaves as a quantum system rather than a large classical one?
Yes, we do not. Yes, I'm sorry, I did not showing the simulation of annealing process, but in my calculation, I doing the just 3 qubits simulation using the this Hamiltonian, but I'm not so sure is about the quantum is. Yeah, of course, the coupler and resonator coupling is just classical circuit. Yeah, just classical circuit. But the qubit is some kind of quantum system. And comparing to the normal this Hamiltonian, this singular Hamiltonian to this full Hamiltonian of this system, we can treat some kind of optimization problem. And we can get the final state of the qubit up and down, corresponding to the answer of this optimization problem. But in your question, quantum classical, sorry, I'm not so sure about the
maybe, sorry, maybe I did not put it properly. So my question is, what is the maximum number of qubits you can directly simulate?
Yes, sorry, that is, I'm not so, I don't have the good PC to simulate this kind of circuit. I just only simulate 3 qubits with resonator. So because we are using the ultra-strong coupling between the qubit and resonator, in that case, the space of the annihilation and collision operator should be 10 or more space. And in that case, it is difficult to simulate many qubits in the normal PC. In that case, I just only checking 3 qubits and 3 resonator.
Thank you.
So, okay. Thank you for your question, Alex. So, any other question or comment? Okay, I have actually a couple of questions. So, especially you don't worry about the Airbridge in your system in both quantum all-to-all coupling, free coupling quantum annealer, as well as the quasi-needy 2D architecture. So, I just wondering that how about the yield of the Airbridge? It's almost 100% yield based on your process.
Yes, now it's almost 100%.
Oh, really? Oh, wonderful.
In this side.
I see. Great. So then the next question, how about the influence of the, for instance, the some crosstalk or reflection at the, you know, the average? It's not so, we have to worry about that, you know, it's
yes, of course, we need to consider the crosstalk between using when we are using this kind of crossing using the averages. And sorry, I did not prepare a slide to showing that result, but in this paper we have some easy, some simple checking the crosstalk between this resonate and this resonate.
Oh, okay, you have checked.
In that case, in the crosstalk is in my memory less than 40 dB. It's,
okay, 40 dB, yes.
Minus 40 dB. Yeah, and this is we can ignore. It seems we can ignore it.
Okay, great. Thank you. Okay, Daniel, please.
Hi, thank you very much. That's a really, really interesting presentation. I just have a quick question. How many qubits is each qubit coupled to? How many other qubits is each qubit coupled to on your design? Because what interests me on your design, it looked as if every qubit was coupled to every other qubit, which of course would be a big advance. Is that the case, or is this just a simplified view?
Yes, that is the problem, and okay, yeah, I know. So we are interested in how many qubits can be contained in the one unit, but optimistically estimation 10 or 20 qubits can be simultaneously coupled, but this one is 8 qubits. This is not so sophisticated design, but this 8 qubits is also difficult, and maybe 10 or around 10 is the maximum.
Okay, thank you very much. Thank you.
So, okay, any other quick questions? So, okay. Okay, so almost time is up. So, okay, so Tomonaga-san, thank you very much for your very wonderful presentation. So we all really enjoyed. So thank you very much. So, okay, Shanice, do you have any announcement on next INQA seminar?
Yeah, so our next INQA seminar will be next week, Tuesday. I'm just going to get up the details. Bear with me, sorry.
Yes, please.
Yeah, so it's next week, February the 21st, and our speaker will be Michael Hanks from Imperial College. And then we also have another seminar the following week, which will be March 1st. Yeah, so I'll send out more details today about that.
Hi, okay. So thank you very much. So I hope to see you again in next INQA seminar. So see you, bye. So Tomonaga-san, ありがとうございました。
Thank you very much. Bye.
Thank you very much.
Thank you very much.
Bye.
Thank you. Bye.
Thank you. Bye.